Hi there. My name is Cameron Harmon. I have been in the ceramic business my whole life. My father was in the ceramic business before me. So I eat, sleep, and breathe ceramics, as it were. But now that I've retired, I figure it's time for me to pass on some of this information to you. And one of the best ways I know to do that is to put together a monthly newsletter containing information that almost any ceramist needs to know. We know that there are people in manufacturing that deal with very exotic materials and hobby ceramists that deal with their own kind of problems. So we're trying to make this with basic information that almost anybody can use. So to start it off, I'm going to give you some information on kilns. I know kilns. I've worked with kilns my whole life. I've designed and built kilns for a living. I've operated my own pottery. I've been in ceramic plants all over the world and have experienced all kinds of problems and have had to solve all kinds of problems. So passing this information along to you, I think, is a very important thing to do. So let's talk about kilns. You know, there are several things that you need to know about any kiln. Whether you're designing the kiln or using the kiln, it's helpful to at least know some of these things. You have to know what is the maximum temperature you want the kiln to go to. You have to know something about what kind of heater that you're going to use to raise the temperature with. You have to know something about the load in the kiln and the way the kiln is constructed. How much of a load does that present as well? Now, it's easy to talk about these things, but it takes people years of experience and calculations to really work out the right way to go. So what I'm going to tell you is stuff that you can probably use to your advantage, whether you are deeply into it or not. So let's start with the maximum temperature. That depends, of course, on the product that you're firing in the kiln. Now, an awful lot of people will have a maximum temperature around, say, 2300 degrees. That's good enough for cone 10 for a hobby ceramist, and 1800 to 2000 degrees, wow, that's good enough for most whitewares. It's also good enough for bricks. Very useful. On the other hand, there are some refractory products that require a temperature of 3200 degrees. Now, each of these requires a different kind of heater and different kind of refractory lining, shall we say. So let's take a look at the heaters. If you have wire coils, they could be made out of a chromel alumel metal, which will allow you to heat to about 1800 degrees Fahrenheit. If you heat them to 2000 degrees Fahrenheit, they'll last once or twice and then burn out. On the other hand, if you use some of the more exotic metals for a heater, you can get them to run up to 2300, 2350, maybe sometimes a little hotter, and they'll give you a reasonable life. On the other hand, you can use metal rods, which are made out of an even more exotic metal, and you can get up to 3200 degrees with those. Or if you're in certain types of specialty ceramics, you might use pure graphite that's cut to make one long piece of graphite as it's made into a cylinder and fired in the absence of air, where there's no oxygen around. The graphite will give you up to 5500 degrees, quite hot. On the other hand, you can use fuel. which would be natural gas or propane. Natural gas and air, usually the burner will give you a temperature up around 3,200, 3,300 degrees. Preheat the air, it could go a little higher. On the other hand, if you're using natural gas and oxygen, you can get up closer to 4,000 degrees. You can use propane and air, that will get hotter than natural gas and air. But it costs a bit more than natural gas. So it all depends on what you need and what you're going to do. Now, you have to reach a certain peak temperature. So let's say that you're going to fire to 2,300 degrees. Well, a nichrome wire is not going to do it because it just can't get hot enough. But you can use gas burners or you can use the exotic metals. They will work fine. And in fact, a lot of the small hobby kilns are made just that way. You may notice that the hobby kiln has a rather thin lining, brick only about 3 inches thick. But you may notice if you see an industrial kiln that a lining is much, much thicker. The reason is that there are things called losses. When you heat up a thin brick, it's going to stop the heat. It won't be 2,300 degrees in the room. But that wall, that supposedly cold wall on the kiln, is going to get pretty hot. On the other hand, if you put a thicker lining in, you can drop that temperature enough to where you can put your hand on the side of the kiln even when it's 2,300 degrees on the inside. Now, it's important to know what the load is, and the load is constituted of the weight of the product you're firing, the weight of the shells or refractory materials you're using to support the product. The weight of the refractory lining is important because heat gets absorbed by that refractory lining, and the heavier it is, the more heat it's going to absorb and the more heat has to be provided. Furthermore, if you have any cracks or openings in a kiln, you're going to lose heat through those openings. Even in an electric kiln, where you don't have a lot of air moving around, you lose heat by radiation. In fact, you can lose a lot of heat by radiation. Now, in a gas-fired kiln, you're going to have a flue opening, and you will lose heat by radiation, but if you construct the flue correctly, you won't lose much heat by radiation, but you'll have hot flue gases coming out all the time. It is interesting to note that in spite of that heat loss in the gas kiln, usually gas kilns are so much more efficient that extra loss is really not going to cost you anything. In fact, a typical hobby kiln, a large one, may be 7 cubic feet in capacity and cost $5 or $6 in electricity to burn. On the other hand, you can take a 100 cubic foot gas kiln and it'll only cost $5 or $6 to burn. Considerably more efficient, even though the losses are bigger through the flue. Now, the other thing to consider is the weight of the wall. In the old days, the bricks were really heavy, solid bricks. You pick one up was maybe 10 pounds for a whole brick. Then they came along with an insulating fire brick where they were able to make that brick very porous, full of holes, and cut the weight down to a couple of pounds. Well, that makes a huge difference in the amount of energy that has to be used to heat up the hot face because it's not so much weight being absorbed by the brick. In fact, in reality, in the whole wall, generally speaking, the difference is 8 to 1. that is, the insulating fire brick wall is only 1/8 the total mass of the old-fashioned fire brick wall. Now we come to fiber, which is even lighter than the insulating fire brick. However, for 2300 degrees, you'll find that the walls can be anywhere from 6 to 10 inches thick, depending upon how cool you want the outside of the kiln to be. Something you need to know is that when you heat the kiln up and you get to your final temperature and you want to hold it at that final temperature, you can use your controls to back off the amount of energy going in, because the only energy you need at that time is just enough to overcome the losses, since all you're doing is holding the temperature. You need a little bit more because you're still heating up part of the load that didn't quite get hot in the first place. But on the other hand, the outer wall is going to keep getting warmer for a while. But there's a thing we call equilibrium. At that point, at the equilibrium point, the temperature of the hot face is fixed, hasn't changed, but the temperature of the cold face also becomes fixed, and it doesn't change. As an example, if you look at an industrial tunnel kiln, where the temperature inside that kiln has been the same for several years, temperature on the outside is also the same. It hasn't changed for several years. So don't get concerned about the fact that the longer it runs, the hotter it gets. That's only true for very short firing. Now, following on that, if you have a lightweight lining and you're able to fire the kiln fairly fast because you don't have so much lining to heat up, then you probably won't use quite as much energy because you're going up fast and you're not heating as much wall and you're not heating as much losses. The outside wall will remain cooler because it hasn't been exposed to the total heat for so long. But if you have a long fire, like 24 hours or longer, that outside wall will get up to the equilibrium temperature, even though it's a lightweight lining on the inside. Now, you have to also consider, what are you going to use to heat the kiln with? As I mentioned, gas becomes very cheap when you get a larger kiln. Electricity is pretty cheap in a small kiln. But there's more to it than that. The way that heat is transferred from the burner to the weir, or from the electric heater to the weir, is different. In the case of the electric heater, it's direct radiation from the heater that heats the weir. That means if you have two pieces of ceramic, one sort of behind the other from the point of view of the heater, then what you'll find is that the one in the back, the one behind, won't heat up nearly as fast as the one that's exposed. So you have to heat it more slowly so that you don't crack the original piece and so that you give it time for that heat to get to the back. On the other hand, if you have a well-designed gas-fired furnace, the heat is going to come from radiation of the products of combustion, and you can direct those products of combustion around the different pieces of wear so that they all heat up pretty much at the same rate. In the center of the kiln where you're going to put your flue, the temperature will be a little bit behind the outside, but not anywhere near the way it is with an electric kiln. However, a gas kiln does cost more to build in the first place. So you need somewhere between 50 or 70 cubic feet of capacity to bring the total cost of construction down to the point where it's more or less comparable to building an electric kiln of the same size. But above that, it gets cheaper faster, no question about it. Finally, the other thing you have to consider is the placement of the load. If you place the load in such a way as it blocks the energy, either from the radiated heating coils or from that products of combustion gas, it's going to slow down the rate of heating. It's going to, in the end, probably give you a kiln that has a very bad temperature uniformity in it. In some cases, the ceramic is very forgiving, and it'll take 100 degrees or more temperature difference and be fine. But sometimes, especially if you are manufacturing precision ceramics, you need a temperature uniformity less than 5 degrees anywhere in the kiln. Well, that's a lot harder to do, but eminently possible. Not a problem at all, really. So your selection of burner type has to do with what it costs you to build it in the first place and what the product really needs in the second place. The reason that there are so many electric kilns with those coils in them is because they're cheap to build, and even though they're inefficient, they don't use much power because they're so small. And you see so many of them because that ceramic that most hobbyists use is very forgiving, and you can be 50 or 100 degrees off and not really get hurt too badly. Got to watch it with your glazes, though. That could be a bit more of a problem. Well, this is just the beginning, just an idea to show you the kind of information we're trying to pass on in our Ceramic Solutions book. If you want to learn more, why don't you go to our website, which is http:// you've heard all that before, ceramics.csiteach.com. Come on over and visit us. Thanks. Bye.